necessary JCL cards. If it is a remote job, it sends it away. Whenever it comes back, it picks it up again for the post-processing. If you don't do it remote, but you do locally, then it executes locally. If you look at it, once again, in a setup, for instance, if you look at the different modules, and this is a slide from 1985, so it is about 7 years old. At that time, we had locally a Sun 3-140, on which just a couple of elementary modules could be done. Modules like BOSAR or stacks had to be done on a local file server. And if we have chosen a lot of degrees of freedom, we would have to go to one of the big computers, which are, at that time, you see, we had a Convex C210. The IBM mainframe is gone. Here we had a Cray XMP, that's now a YMP, and the National Laboratory doesn't have a NEC SX2, but a NEC SX3 with 2 processors. So everything moves up. What are the type of computations that we can carry out? Now, once again, if you read this slide, if you go this way, the analysis gets more complicated. What is the first one? Buckling of perfect shell. There is an approximate solution technique, and here there are crosses for the different loading conditions for which there are operational members. Meanwhile, we also have members for bending, so you also can put a cross there. Higher level analysis modules can do that rigorously. That means that they also satisfy the boundary conditions. If you want axisymmetric imperfections, once again you have approximate or rigorous, asymmetric imperfection, approximate or rigorous, two-mode imperfection where you have both axisymmetric and asymmetric, and then the top, when you have multi-mode imperfection, let us say a double Fourier series. And going this way, you have the different loading conditions, axial compression, external pressure, torsion, bending, and the combined. Okay, now, what type of theories I have been talking about? I will show you, I guess, only 2 slides where I try to summarize some of the theoretical results. One of it is Coite's imperfection sensitivity theory for axisymmetric imperfections. What do I mean by an axisymmetric imperfection? I mean that the imperfection, the deviation from the perfect shape, divided by the wall thickness is equal to an amplitude, a normalized amplitude, cosine I, which is an integer, number of half waves in the axial direction, pi x over L. Now, notice it is I classical. This is a property of every shell, and it can be calculated out of this formula. You will say, well, chances are that that is not an integer. Yes, it will be a coincidence. If you plug in your numbers, you get an integer. But if it comes out to be 17.6, I mean, you decide and you say that's 18, not 17.6. Why 18 and why not 17? Because Coite has shown that if you want to have bifurcation from this pre-buckling state into an asymmetric mode, this is a bifurcation mode, the mode in which a shell shall buckle, you will have number of half waves in the axial direction and a number of full waves in the circumferential direction, given by the integers m and n. There is one restriction. M has to be 1/2 I classical. I classical being the wave number of the given initial imperfection. If this is not satisfied, then there is no strong coupling between the different effects, and you won't get this decrease with increasing imperfection. And you notice, if this holds, then I must always be an even number, right? Because m has to be an integer, so that's a restriction. And that's why when I said 17.6, I didn't select 17, but I selected 18, because 18 is an even number. Okay, here are 2 curves out of publications from Coite, general theory, that's his PhD thesis in 1945, in Dutch. There are two English translations, one by the Air Force Scientific Office, done by Dr. Edward Rix, who himself is a Dutchman, Stanford PhD. So if you have to select which one, the other is a NASA machine translation. If you have a choice, you should take the Air Force one because it is better. Special theory is a paper from Koiter from 1963, which was published in the Proceedings of Dutch Academy of Science in English. So that one is in English. Okay, now you might say that having an axisymmetric imperfection, very short wavelengths, what I have shown there, is as improbable as having a perfect shell. So another possible imperfection is an asymmetric imperfection, right? As a matter of fact, you say, well, I would like to investigate the effect of an imperfection which has the same shape as the buckling mode, and the buckling mode was asymmetric. So you notice this is precisely the same as the buckling mode before, except that I put a bar there and a bar there, indicating that those are now given imperfections. Now, in this particular case, if you solve the problem, it is the buckling occurs at a limit point, and people have shown, Koiter himself has shown, but this comes out of a paper for Hutchinson and Amazigo, that you can write the buckling load at the limit point by this formula, and you see there is a factor there, B. And B is the second post-buckling coefficient. I will show later on a slide it more precisely. It is a property of the perfect shell, and it better be negative, or otherwise we have no real solution, right? Because you have the minus 3B. And what I have here is a plot taken out of the paper from this gentleman here, and what it shows is B for a certain Stringer-Stiffen shell, where does Buttorff Z-parameter. What is Buttorff Z-parameter? Is a length squared divided by the radius and the thickness times 1 minus nu squared, where nu is Poisson's ratio. Now, they did these calculations and they got a curve like this, using membrane pre-buckling, and the trigonometric functions approximately satisfied SS3 boundary conditions. Well, this result was presented and they got jumped upon by all the experimentalists present, because what this indicates, that the Stringer-Stiffen shell under axial compression, if it is rather short in this region here, is very imperfection sensitive. And people have not observed that experimentally. As a matter of fact, they have run very big series of experiments where they took, for instance, at Technion, Professor Singer, they took a seamless tube of a fair length, they machined the stringers into it on the outside, and then they cut it up into smaller and longer pieces, saying that imperfections are about the same, and they didn't detect this. Okay, Hutchinson repeated this with a graduate student of his in 1969. Frauenthal was his name. And what they did, they then used nonlinear pre-buckling, also SS3 boundary condition, rigorous, so a second level solution. And what happened is that this big peak disappeared. They got a curve that looked like that. They also did it for C4 and did that curve there. So those are level 1 and level 2 solutions that are in this deco. You can use it. Now, I talked just about this asymptotic perturbation expansion. What do I mean? There is a small parameter xi, which is the amplitude of the buckling mode. In the low deflection space, you write it like this. This is the first post-buckling coefficient, that is the second post-buckling coefficient. They are properties of the perfect shell. If you use Donnell-type equations, you can cast it in a form where the dependent variables are W, out-of-plane displacement, F, stress function, and then you have the zeros order state, xi times the first order state, xi squared the second order state. And you have to then solve for those quantities and evaluate these post-buckling coefficients. This all has been done in the literature. So the interesting thing is, here I show you then why you